Today I will continue my search for the perfect audio. In previous videos I have tested my operational amplifiers and audio amplifiers. I have chosen the best one, and today I'm going to be looking at the acoustic systems. So I have those four types: the cheap one, the expensive one, and the old style one, and the headphones. So the headphones probably are providing the best sound quality subjectively, but we will see if it's true or not using our measurement techniques. So I also have built the audio amplifier, so that from the previous test I found out that this one is the best audio amplifier with the total harmonic distortion only 0.006%, which is almost the same if I replace this amplifier with a single piece of wire, so as good as the wire. So we just added this power supply, classical style, and a bank of capacitors, and the amplifier itself. To test the acoustic systems, I'm going to use those microphones. So the simplest one is that one, just microphone itself plus the internal FET transistor. So this chip is used for the digital output, basically the comparator not doing anything to the sound itself. So this one is based on the amplifier Max 9812. So here's the amplifier. There's also the control of the voltage. So it has one chip which might introduce some distortion, but we will see. And the last one is a device I have built. It also has the internal FET transistor and also has the small transistor for the amplification. So those two is amplifiers, and this one is just a single transistor. Now I'm going to test the first microphone. So the microphone is connected to the computer and to the oscilloscope. So with the oscilloscope I can look at the signal level at the sound card. This amplitude of the signal should not exceed 1 volt, and the signal from the sound cards is displayed on this spectrum graph. I'm using the right room equalizer wizard for this purpose. So once I start to increase the sound, I play 1 kHz, and I'm going to see the main peak at 1 kHz, second harmonic, and third at the multiples of this frequency. So let's do that. So first, yes, we have to start generation. And we know that we have this main peak at 1 kHz and a small signal at the sound card, 0.2 volts. Let's increase the signal. Now we have third, second, third, and fourth harmonics. And the signal amplitude is 0.5 volts. Let's increase it once again. The sound card is overloaded, so the generation stopped. But we can start it once again. Should not exceed 1 volt at the sound card input, otherwise the system stops. .4%. If we go down, zero 0.25%. Go up. .4%. Okay, so up, down. So we play with this signal. When the level is low, we see that like we have the noise level up which is similar to the, actually my voice is the noise level generator. The voice is comparable with the main signal, 1 kHz, but if I increase the signal, my voice is not so prominent any longer. Yeah, anyways, so to conclude those results, so what we see that if we increase the sound level, we're going to see the increase in total harmonic distortion coming from the speaker. However, we should note that we have to decouple this distortion. One source of distortion is speaker itself, and second one is microphone. So we have to minimize the distortion caused by microphone so that we can measure the actual distortion from the speakers. How to decouple the microphone distortion from the speaker distortion? Well, the first step would be to choose a microphone with the minimum distortion. So we have different two types of microphones. This one has the amplifier, a small microchip. This has no amplifier except the transistor on board. And that has one transistor that I built this amplifier a long time ago. It's pretty good, but it has one transistor and circuit is pretty simple. So considering that they have amplifiers, you might expect that those devices have distortion. So the idea is that when you have the small signal, then probably the device is more or less linear. So how to find the distortion of microphone? So if I've noted that if I approach the microphone to the speaker, the distortion level is rising. And this might happen only due to the fact that microphone has distortion which is proportional to the signal coming to the microphone. So what I'm going to do, I'm going to start moving the microphone from the speaker far away until I reach some level at which the distortion is not going to change. So distortion is going to be dropping once I move it away, because the signal is going to be reduced, and in some position probably it's not going to change because the device is in the linear regime. So this is the idea, and now I'm going to do that. Let's test the second microphone. I'm going to raise the output voltage. So as we have seen, the voltage at the output of this device is 0.1 volts. It's way too low for the sound card. Probably going to have some noise with this signal, so it's not good for the processing device. And secondly, the distortion of this device is pretty high. It's around 2.5%. So those two devices are comparable. The distortion are comparable, just slightly high distortion for that one. But the difference is that at the output of this device we have nice signal, around 1 volts. In that case we have 0.1 volt. So it's way below the expectation. So we conclude that this device is garbage and we stick to that guy. The last microphone that I built. Let's increase the signal. So to conclude, the distortion is pretty high, around 15%, and the signal at the output is not actually sine wave. Let's look again. So the output signal is distorted, and that means that the reason for the high distortion is actually amplifier I've built. It has very high coefficient, but maybe some mistakes in the design. so it does cut the sine from one side. It's not good amplifier with high distortion, so this is garbage. To conclude, among those three microphones, only that one is acceptable for our use. Has good output signal and acceptable distortion level, around 0.2, 0.4%. That one has similar distortion, but the output signal is very low, not good for the measurements. This device has huge distortion, so it's not acceptable for the measurements. Here is the first test. So we see distortion 0.4%. We see the input signal at the level 0.3 volts. That's all good. And now let's run the test. Alright, mark on audio analyzer software. So I have the software here. So press this button. Start test. You see the signal is generated. Various waveforms. The results are ready. So press OK. Now we can look at the distortion level, in this case 0.8%. Show graph. Also, it's fun to see the frequency response. Second experiment. Distortion 0.5%, slightly higher. This is the last experiment for the day. And we know that total harmonic distortion is almost 8%. And I use those speakers for the reference because I know that those are not good, but garbage speakers, and I do see the difference. So the difference is 0.2%. Okay, I have assembled all the results in one single file for the reference in the future. And now I can come to the conclusion. So the conclusion is a bit unexpected. I was thinking that speakers introduce audio system introduce significant distortion. I was thinking that probably about 5% distortion is introduced by the speaker, but the opposite is true. From the measurements, I came to the conclusion that the distortion is approximately 0.2%. Total harmonic distortion is 0.2%, and probably is caused by the microphone. So why I'm thinking so? Why do I make this conclusion? Because if I keep the voltage at the acoustic system constant, then the distortion is also constant. But when I move microphone, if I approach to the speaker, I'm going to see the increase in the total harmonic distortion. If I move it away, I will see fall of total harmonic distortion. So meaning that the main contributor to the distortion is actual microphone, not the speaker itself. But even at 0.2% distortion, it's pretty good. So I don't think you need anything else. You can ask anything else from this system. And in reality, maybe this number is even 10 times less. So let's say 0.02%. So I put all the results comparison in one file, so we can compare the distortion, total harmonic distortion for different speakers, and the numbers are not significantly different, like maybe difference is 20%. So the harmonic distortion is very small. The only difference is the intermodulation distortion. And the difference happens because I have those systems with different number of speakers. In that case, I have 3 speakers working at 3 different bandwidths, 2 speakers and 1 speaker. So in the case, if I have 1 speaker on the system, then I might expect to have the intermodulation. If I have 2, then it's different frequencies for each speaker, so there is no way the frequency from one speaker can link to another one. Can be linked into another one. So in that case, I have 3 of those, and in that case, there is almost no distortion. So if you look at the graphs, so this is the distortion, intermodulation. So I know that for instance this one, so blue one has 3 speakers inside, there is almost none. Green one has 2, and the blue one has just 1. Speaker. So now you see the distortion. So meaning that like if I submit to frequencies 60 Hz and 7 kHz, I'm going to see the intermodulation of 7 kHz. So it's 7 kHz plus minus 60 Hz, as I described in my previous video. But even with this type of intermodulation, it's still pretty small, minus 6 dB. So it appears to be that the speaker does not have the tendency to have this intermodulation or total harmonic distortion. So once again, to summarize the result, we can say that the acoustic system is way better than I was expecting. Total harmonic distortion is 0.2% and probably is even less than that. The distortion probably caused by the microphone, and in reality the distortion might be 10 times smaller. So there is not much you can ask from the acoustic system except the proper design, because if the design is silly, you might have some bumps and dips in the frequency response, or you might have let's say 1 speaker inside of the acoustic system, so you might find some intermodulation. But if you have a nice system with 3 speakers and you have nice frequency response, then that's all you need. Distortion is small and is comparable with the distortion of audio amplifier. And the difference of distortion, it's cannot be detected by the human ear. Like if, for instance, you look at the internet, you can find the tests, and you can try to detect the second harmonic. If it's below 40 dB, there is no way you can hear it. And even in this, the worst case, you have just single 1 speaker, the intermodulation distortion is beyond 60 dB. So it's beyond human comprehension. And at this moment, I think I should stop this project because I'm limited by the hardware. To run the tests on those devices, you have to have very linear microphone, and I'm not sure you can get one because like it's kind of chicken and egg problem. To test microphone you need speakers, and to test speakers you need microphone. So I don't see a way how to solve this problem. And secondly, there is no need to do it, because even at the distortion level of 0.2% total harmonic distortion, it's more than good enough, so you don't need anything else.